In this video, we are continuing our final review and talking about optimization. So we've learned 3 techniques for optimization problems. So remember, optimization just means to minimize or maximize something. Okay, so the first technique that one of the 3 techniques that we've talked about involves finding local mins, local maxes, and saddle points of a function f using what was called the second derivative test. So second derivative test. Okay, so I won't state the whole second derivative test here, but as a reminder, this was in section 14.7. Section 14.7 is where you want to look to review this second derivative test and what it said. Okay. Another technique we learned for optimization problems was to find the absolute min or max of a function f over a closed, bounded region. And I care that you understand what closed and what bounded means. So bounded means it doesn't go off to infinity anywhere. Closed means it includes whatever the boundary of the region is. Okay. So our method for dealing with optimization problems like this involved, we first find the critical numbers of f in the region. So we don't care about the critical numbers that might lie outside the region, because we're just trying to find the min and the max over whatever this closed bounded region is. Okay, and then after that, so next, we find the possible extreme points of the boundary. So find the possible extreme points of the boundary. All right, and after we have those, after we have the critical numbers that are in the region and the possible extreme points of the boundary, then we plug these into the original function. So these critical numbers, these possible extreme points on the boundary, they're the candidates where this absolute max and this absolute min might happen. So you take the candidates, you plug them into the original function, and when you do that, the largest output that we get is the absolute max, and the smallest output is the absolute min. Okay, and we talked about this as well in section 14.7. Okay, so review section 14.7 and the example that we looked at there to remember, how do we do this? How do we find critical numbers? How do we find the possible extreme points on the boundary? And then what did we do after that? Plug them into the original function. All right, so there's one final technique for max-min problems that we've learned. And this technically involves finding local mins and maxes of a function f that's subject to a constraint, which is typically written g of x comma y comma z. I'm just assuming there's 3 variables, but it could be any number of variables, equals 0. And this method was Lagrange multipliers. So Lagrange multipliers to maximize or minimize functions with a constraint. Okay, and this was in section 14.8. All right, that was section 14.8. So sometimes Lagrange also works to find to find absolute extreme points. So absolute extreme points just means we could be talking about the absolute max or the absolute min or both. It just depends on the context of the question. All right, so let's do a practice problem now. Okay, so the question I want to look at is from the final practice problems, part 1, question number 5. So the question says you are in charge of erecting a radio telescope on a newly discovered planet. To minimize interference, you want to place it where the magnetic field of the planet is weakest. The planet is spherical with a radius of 6 units. Based on a coordinate system whose origin is at the center of the planet, the strength of the magnetic field is given by this function. Where should you locate the radio telescope? Okay, first thing that I want us to do is pause the video and try this for at least 5 minutes. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 5 minutes. So just as a heads up, this is a long problem. Even 5 minutes is probably not going to be enough time to finish the question. So if you need to give yourself 10 minutes, 15 minutes to try this, please do. So in some sense, the most important time in these final review videos is this time right now that you're using to pause the video and try these problems on your own to see how well do I understand this material. Alright, so hopefully you've done that. Hopefully you've paused it for about 5 minutes to try this. Let's start to talk about this together. So the first thing that would be helpful to know is, do I want to maximize something or minimize something? So the key word there is, it says the magnetic field needs to be the weakest at whatever this point is, if we're trying to minimize the interference. So if I want that magnetic field to be the weakest, I want to minimize our function. Okay, so our function m, let me write it like this. M of x comma y comma z equals 6x minus, I'm just copying it down, minus y squared plus xz plus 60. I want to minimize this, and the thing that I want to minimize or maximize, we call that the objective. So this is the objective right here. And then there is also another condition. It says that this point x comma y comma z needs to be on this spherical planet. And it tells us it's a sphere with radius 6. So we also have a constraint. We are given a constraint. And it tells us where to make the origin. It says, let's make the origin be the center of the planet. Okay, so that constraint is x squared plus y squared plus z squared equals the radius squared. And radius is 6, so 6 squared. And if we move all the terms in the, if we get one side equal to 0 in the constraint, that's what we call the function g. So g of x comma y comma z is equal to x squared plus y squared plus z squared minus 36. That's what we get if we move that 6 squared over to the left, so the right's equal to 0. All right, so next I need to find some gradients. So the gradient of m is 3 variables. It would be the partial with respect to x, comma, the partial with respect to y, comma, the partial with respect to z. Okay, and then evaluating this, the partial with respect to x is going to be 6 plus z. The partial with respect to y is negative 2y. And the partial with respect to z is x. Okay, so similarly, if I take the gradient of g, this one's easier. This is going to be 2x, comma 2y, comma 2z. Okay. So one thing that's helpful to think about in these optimization questions is, because in this problem, ultimately what it just said was, it said the word weakest. And that told me I was looking for a min. If a problem doesn't specify if it's a local min or an absolute min, it means it's an absolute min. It wants the weakest point for this magnetic field, which is the absolute min. Okay, so one thing that's helpful to look at is, even when I'm doing a Lagrange problem, to think about the constraint and see, well, is the constraint a closed bounded region? So this constraint is the surface of a sphere, and the surface of a sphere is closed because it contains the boundary of the sphere. It's the surface of it. This is bounded because the surface of the sphere doesn't go off to infinity. It's a closed bounded region because it's a surface of a sphere. So we're trying to minimize this function over a closed bounded region. So this should have an absolute max and min. If our constraint wasn't a closed region, or maybe it wasn't a bounded region, then it doesn't necessarily need to have both of them. It could have an absolute max and not a min, or vice versa. It could technically also have neither. Alright, so let's keep going with Lagrange. Alright, so next we want to set the gradient of m equal to lambda times the gradient of g. So when we do that, we'll get several equations. We'll get 6 plus z equals lambda times 2x. We'll get negative 2y equals lambda times 2y. The third one is we'll get x equals lambda times 2z. So I got these, looking back at the previous page, I got these by looking at the components of the gradient of m, like the first component was 6 plus z, and then setting that equal to lambda times the first component of gradient of g. So lambda times 2x is equal to 6 plus z. And then that was my first equation. And then I did the same thing with the other components. Okay, so there's one more equation I get to write down, which comes from my constraint. X squared plus y squared plus z squared equals 36. Okay, so we have the system of four equations. System of four equations and four variables, x, y, z, and lambda, that we want to solve. So in these Lagrange problems, there's two parts that are particularly important. One, I would say, is the setup, where you identify what your objective is and what your constraint is. And that can be sometimes tricky to do, especially when we have these word problems. So that setup is important. And then also solving this system of equations is important. So if you didn't make it this far when you paused the video before, pause the video for about 3 minutes at least to try this. That's probably not going to be enough time to solve this system. This is actually kind of the heart of the problem right here. So I would really focus most of your time on trying to solve this system. But try to pause it at this point. 4, 3, 2, 1. Pause that video and try this for about 3 minutes. Alright, so hopefully you've done that. Hopefully you've paused it. So let's talk about how we can solve this. So looking at these equations, the equation that looks maybe the easiest to try to simplify to me is equation 2, because I see y on both sides. So remember, the temptation is to divide both sides by y, but we've talked about that if you divide both sides by a variable and it cancels like the y would, we might lose an answer. So never divide both sides by a variable. If you didn't remember that, definitely write that down somewhere in your notes. I'm not writing it down now because we've written it down before, but write that down somewhere in your notes. Never divide both sides of an equation by a variable to cancel something away. That might make us lose a solution. So instead, if I look at equation 2, let's move everything over to one side. So I'll get 0 equals 2 lambda y plus 2y. And then factor that thing out. So we can factor to 2i and be left with lambda plus 1. And now at this point, there's two possibilities. Either this first thing equals 0, so either y equals 0, or this second thing equals 0, which would mean lambda is equal to -1. So notice that if I divided both sides by 2y, I would have missed this first possibility where y equals 0. And that would have been bad. I would have lost possible answers. That would have been a major error. Okay, so we have these two possibilities that we need to consider. Y equals 0, and then when lambda equals -1. Okay, so I got to consider two cases. First case, I'm going to say y equals 0. Let's consider that case. So in this case, what I'm going to do is I'm going to plug this value in to these equations to simplify them. So with the first equation, if I plug in, so actually with the first equation, there's no y in it. So I can't plug in 0 because there's no y to plug into. And in fact, in the third equation, there's also no y. So what I can do in those equations is, let's isolate lambda. So in the first equation, I'll divide by 2x and get 6 plus z over 2x equals lambda. If we do the same thing in the third equation, we get x over 2z equals lambda. So how come here it was okay to divide by a variable? Well, here, when I divided by a variable like 2x or 2z, I didn't get cancellation happening. So I didn't sort of cancel away an answer. So that's the difference between what I did above and what I did below. Okay. If I were to plug 0 into equation 2, it wouldn't really help me because I just get 0 equals 0. Okay, so let's work with these two equations that I have here. I can set these equal because they both equal lambda. So we get 6 plus z over 2x equals x over 2z. And if I cross multiply, we get 12z plus z squared equals 2x squared. Okay, so I actually forgot. Whoops, okay, there we go. So I forgot to put a 2 in front of the z squared. Okay, so this is 2z squared. All right. Okay, so I have an equation in terms of two variables now. So I haven't worked with equation 4 at all. Let's plug y equals 0 into equation 4. So if we do that, equation 4 becomes x squared plus z squared equals 36. Okay, so we got x squared plus z squared equals 36. And now what I can do is I can isolate one of the variables here. For example, x squared equals 36 minus z squared. And if we take that and now we substitute into this equation above it, we will get 12z plus 2z squared equals 2 times x squared, but I know x squared is 36 minus z squared. So overall, we have 12z plus 2z squared equals, distribute the 2, 72 minus 2z squared. So let's rearrange this. If I move the z squareds to one side, we'll get 4z squared. Let's keep the 12z there, and then subtract 72. So now I could divide everything here by 4, and I'll get z squared plus 3z, and then minus 18 equals 0. And I could factor, I could factor this. This is z plus 6 times z minus 3 equals 0. So we get two possibilities. Either z equals a negative 6 or z equals 3. All right, so let's consider both of these. So if z equals negative 6, so remember in this case, we know what y is. Y is equal to 0. Okay, and now I'm assuming that z is negative 6. So it's left for me to figure out x. So if z is negative 6, I can plug that into equation 4 to get x. So we'd get x squared plus z squared. So that's going to be negative 6 squared equals 36. So I have 36 on both sides. So these will cancel if I subtract. And so I get x squared equals 0, and that means that x equals 0. Okay, so the other possibility is if z equals 3. So if z equals 3, then we get x squared plus 3 squared, x squared plus 3 squared equals 36. And if we simplify and rearrange this, we'll get that x equals plus or minus root 27. Or in other words, this is plus or minus, 3 root 3 if I simplify it. Okay, so from this case, I'm going to call this case 1, we had two possible points. So for case 1 possibilities, there are 2 of them. So the y-coordinate is 0 on these. Okay, so in the first one, z was negative 6. In the second one, y 0 again, but z is 3. Okay, so when z was negative 6, x is 0. X is 0. And when z was 3, x can be actually 2 values. Either x could be 3 root 3, and I'm going to get one more, negative 3 root 3. And then y is still 0, and z was 3 in this situation. Sorry, I should have said there's actually 3 possible points here in case 1. Okay, so now, so remember, okay, I'm going to go up a little bit. We kind of started up here. We started up here, and from working with this equation 2, we got 2 possibilities. Either y is 0, which we just did, or z equals negative 1. Okay, so now we got to consider the case where z equals negative 1. So case 2, which is z equals negative 1. Okay, so this case, I'm going to leave for you to try. And so I'm going to ask you to fill in the details, and I'm just going to write down what we end up getting at the end. I actually think case 1 is the harder of the 2 cases, so I think case 2 is easier. And I kind of did that by design. I wanted to work out the harder one and leave the easier one for you to go back and then try. Okay, but so if we work this out, what we end up getting is that the case 2 possibilities are negative 4, 4, 2, and negative 4, negative 4, 2. So we have 2 possible points in case 2. Okay, so what I need to do now is, now that we have these possibilities, let's plug these candidates into the original function m. And we already determined at the beginning that this particular problem was definitely going to have an absolute max and an absolute min, because we were trying to minimize something on a closed bounded region. Okay, so let's plug these candidates into m to figure out, well, what is that absolute min? Okay, so let's remember that our function m of x, y, z was equal to 6x minus y squared plus xz plus 60. So we're going to be plugging these values into this. Okay, so let's, and I've also just copied down those 5 points below, so I don't have to keep scrolling back down to see them. Okay, so first let's plug in negative 4, positive 4, 2. So I get 6 times x, so 6 times negative 4, minus y squared, minus 4 squared, plus x times z, so plus negative 4 times 2. Oh, and then plus 60. Okay, so if we work out what this is, we get negative 24 minus 16, so that's negative 40, and then minus 8, that's negative 48. So negative 48 added to 60 is 12. So now if we plug in the next point, if I plug in negative 4, 2, If we plug this in, the only thing that changes is the y value. But when I square it, we're going to get the same thing. So if you plug this in and work out what it is, you'll get 12. Okay, so now let's plug in 0, 0, negative 6. So we'll get 6 times x minus y squared plus x times z, so 0 times negative 6, plus 60. So I have a bunch of zeros and then added to 60, which is 60. Okay, so we have 2 more points to plug in. Alright, so we need to plug in, 3 root 3, 0, 3, and we need to plug in negative 3 root 3, 0, 3. So if I plug the first one in, we'll get 6 times 3 root 3 minus 0 squared plus 3 root 3 times 3 plus 60. Okay, so here I have this 18 root 3 plus 9 root 3. So that's 27 root 3, and then plus 60. And then if you plug in the next value, you'll get 6 times negative 3 root 3 minus 0 squared plus negative 3 root 3 times z, so times 3, and then plus 60. Okay, so this ends up being negative 27 root 3 plus 60. So looking at these numbers, the largest of them is this value. So we can tell that this is going to be the absolute max. And again, Lagrange problems typically find local mins and local maxes. But in this problem, because I was optimizing over a closed bounded region, we know that there's supposed to be an absolute min and an absolute max. So the candidates that we get from Lagrange should contain the absolute min and the absolute max among them. Okay. So for a value like this, we can actually compare this with, basically we need to know, is this smaller than 12? And it's possible to check that without a calculator. I could sort of ask myself, well, between 12 and sort of mystery sign here, and negative 27 root 3 plus 60, which is bigger. If I rearrange this, we get 27 root 3, mystery sign, 48. And then if both of these are positive, so if you square both sides, it won't change the sign. If you square both sides, you'll end up getting rid of the square root. And it'll turn out, if you work this out now, if you were to square both sides, that the sign is like this. 48 squared is a bit bigger than 27 root 3 squared. Okay, so what that meant was, going back, 12 is smaller. So 12, is our absolute min. This is where absolute min is. Okay, but the question wanted to know, well, what is the location? What is the point? So where should that be located? We were trying to locate a telescope here. Locate the telescope at either, there's 2 possible places where the absolute min could happen. At either negative 4, positive 4, 2, or negative 4, negative 4, 2. Alrighty. Okay, so the next example, I'm going to do a review of linearization.